Now hopefully you've got your revision under control and you are making great progress towards paper 1. But if you're struggling to know where to start and need to maximise your maths in minimum time, then you should sign up for my rapid revision programme, Upgrade, as you can use it to build your very own personalised revision plan. Which means all you need to do is complete my revision quiz and you'll know exactly which lessons or topics you need to work on to maximise your maths in minimum time. This is my paid programme, but you can sign up for a free trial on my website now. And if you feel like you need top tier support direction from me, then sign up for my live weekly interactive lessons, which include revision specific lessons focusing on the topics that I expect to appear in exam papers 1, 2 and 3. Right now there is a special offer, and the next 20 people who sign up for live will get 100% free access to my upgrade programme as well, which means that you will have complete access to all the best resources that can help you achieve the grades you need to take you on to the next phase of your educational journey. Okay, welcome to this video. We'll be having a look at the first practice paper for the 2025 exams. We're going to be having a look at a paper 1 non-calculator higher tier paper. As always, you can download this booklet from the description. There will be a QR code on the booklet so you can get back to this video at any point. But obviously just remember that we are going to be covering a selection of topics here, and you do need to make sure that you do a full coverage because there's no guarantee that this will be anything like the actual exam, but we'll be going through a good selection of topics and there will be links in the description for you to get a full coverage of lots of other topics that aren't included in this booklet. Okay, so we're going to be starting with this first question here, which is to express 84 as a product of its prime factors. So for a product of prime factors, we need to make sure we get that first two numbers correct. So when we go for 84, we want to make sure that these first two numbers, I'm going to go for 2 and 42, are definitely correct. So 2 is a prime number. 42, we can keep going with the 2, so 2 and 21. And then we're going to have to think of two other factors, so 3 and 7 for 21. And there we go, that gives us our prime factors there, all circled. So our answer we can write in one of two ways, 2 times 2 times 3 times 7, or the two 2's here can be written as 2 squared. So 2 squared times 3 times 7. Either one of those answers, absolutely fine for your final answer, but of course only give one of them. And there we go, question 1, product of prime factors. Question 2 here, we are dividing decimals. So we have 47.85 divided by 1.5. And it says to give your answer as a decimal. So we want to take the decimals out here. We're going to do 4,785 and divide it by 15. To do that, we'll use bus stop division. So 4785 divided by 15. I'll write out some of the multiples of 15. There we go, and if we need to go further, I can write some more. 15 goes into 47 3 times with a remainder of 2. It goes into 28 once with a remainder of 13. And I'm going to have to go a little bit further now. So 105, 120, 135. There we go. So 1, 2, 3, 4, 5, 6, 7, 8, 9 times. 319 is my answer there. So to figure out very quickly where that decimal goes, rather than thinking about the change of place value that we've done in terms of this division, I can just estimate the answer for this. So if I was to estimate the answer, it would be 50 divided by 2, which is 25, which gives us a really good, quick indication of where that decimal needs to go. So it'll be 31.9, as that value there was obviously close to 25. So there we go, my final answer, 31.9, and there is dividing decimals. Question 3 is looking at fractions, percentages and ratios. So here we have Emily has 360 flowers. The flowers are lilies, tulips, daffodils or roses. 3/8 of the flowers are lilies, 35% of the flowers are tulips, and then the daffodils to roses are in the ratio 4:5. Work out the number of roses Emily has. So we want to take this in stages. We're going to first work out the 3/8 of 360. So 1/8 of 360 is going to be 360 divided by 8. Take our time to work this out. 8 goes into 36, 8, 16, 24, 32. So 4 times with a remainder of 4, and then it goes into 40 5 times. So 3/8 will be 45 times 3. 3 times 40 is 120, 3 times 5 is 15, so 135. So there we go, we have 135 lilies. If we move on to the tulips, we have 35% of them being tulips, so 10% is 36, 5% is half of that, 18. We want 3 of the 36s to make 30%, and then the 18 as well. I could just do column addition for that, so 36, 36, 36 and 18. Add these up, 6, 12, 18, plus the 8, 26. 3, 6, 9, 10, 12. So there we go, 126 tulips. The remaining flowers are in the ratio 4 to 5, but I need to figure out what this is as a total first. If we add those together, that's 261. So if we figure out how many flowers are left over, we have 360. Take away 261. We could use column subtraction for that, but I think it's relatively nice there that there's 99 left over, and they are in the ratio 4 to 5. So daffodils and roses in the ratio 4 to 5. So we have daffodils to roses, 4 to 5. That's 9 parts in total. So divide that by 9 is 11. And then we'll want to multiply both of these by 11, which is 44 and 55. We wanted to know how many roses there are. So the roses is the 55. And there we go, that's our final answer, 55 roses. So being really confident there with fraction of an amount, percentage of an amount, and of course sharing in a ratio. And there we go, final answer, 55. Question 4 is looking at a scatter graph. So whenever we have a scatter graph, I would basically always draw a line of best fit pretty much straight away. We want to get a point there which is pretty much going through all the points with a few below and a few above. So there we go, I'm quite happy with that line of best fit. There is quite a few different ways that we could draw it, ever so slightly different angles, but as long as it looks good, we're happy with that. So it says one of the points is an outlier. Write down the coordinates of this point. So clearly we can see there is a point over here, which is far away from the line of best fit, and we want to get the coordinates of that. So down the bottom, that's at 10, and to the side, that's at 19. So the coordinates for that would be 10 and 19. Part B says to describe the relationship between the maximum temperature and the number of hours of sunshine. So careful on this one, that's talking about the relationship, not the correlation. If it said correlation, well, this graph has a positive correlation, but it says to describe the relationship. When we describe the relationship, we just use the words on the axes here and say what happens as one of them goes up. So for example, as the number of hours of sunshine goes up, the maximum temperature goes up. Of course, if it had a negative correlation, it would be the other way around. As one goes up, the other goes down. But as this has a positive correlation, it's as the number of hours of sunshine goes up, the maximum temperature goes up. So there we go. We won't write that out, but there we go. There is a description of that relationship. It says on the same day in another town, the maximum temperature was 17.6. Estimate the number of hours of sunshine. Again, we're only estimating it because we are using a line of best fit. So let's go to our graph. Let's find where 17.6 is. That's where 17 is, just in the middle there. So if this is 17, 17.2, 17.4, 17.6, we can go across to our line of best fit. We can go down then, following that very, very carefully, of course, using a ruler. And then we can read this number. Well, that is 14 in the middle there. It's just before that, so that is 13.8 on my graph. Obviously yours will change depending on your line of best fit, but I get 13.8 hours. And there we go. So using the line of best fit there, really carefully tracing along, of course using a ruler and a pencil for that, and just make sure you leave that line on your scatter graph to show that really clearly that you've read from the line of best fit. Question 4 is looking at probability from a table. So it says a bag contains blue, green, red and yellow and a marble is going to be taken at random from the bag, and the table gives us the information. This particular table gives us some algebra for red and for yellow. It says red is 2x and yellow is 1x, which means that red is twice the probability of yellow. However, it does just say to find the value of x here. So what we need to do is remember that these numbers in the table add up to 1. At the moment, we are only given these two, and together they add up to 0.52. And 1 take away 0.52 gives us the remaining value, which is 0.48. And that is shared between these two here. So 0.48, there is a 1x and a 2x. So in total, there's 3 x's there. So we want to divide that by 3. I could just do the whole number 48 divided by 3, which is 1, 6. So that's 0.16. 0.16, and that's the value of 1x. Of course, if we needed to, we could write them in the table, and this would be double that, so 0.32. But there we go, the value of 1x there being 0.16. It says for part B, if there are 64 blue marbles, work out the total number of marbles in the bag. Now don't forget these decimals in the table are just hidden percentages. So here where it says 64 are blue, well, that just relates to this 0.32, which is 32%. So if we write that down below, that 32% is equal to 64, and we want to know the total, so we want to know what 100% is. To do that, we can divide down to 1%. So if I divide by 32, I get 1% is equal to 2, and then times that by 100 to get my 100%, which is equal to 200. And there we go, a bit of a reverse percentage there within our probability from our table. Okay, on to question 6. It says 2 alarms ring together at 6 AM. One rings every 18 minutes, the other rings every Z minutes. They next ring together at 7:12. Find the smallest possible value of Z. Now, first things first is we need to know what the actual amount of time is here. Otherwise, we're not going to know what to look for. So from 6 to 7:12 is 1 hour and 12 minutes. Of course, 60 minutes in an hour, so 60 plus 12 is equal to 72 minutes. Now, whatever number this Z is, it has to be a number which fits perfectly into 72, or a factor of 72. So if I write out the factors of 72, it'll have to be one of these numbers. 2 and 36. 3 goes into 72. Again, you can always just do these quickly to the side. It goes in twice, 24 times. There we go, so 3 and 24. 4 goes in half the amount of times that 2 does, so 18 times. 5 doesn't go in. 6 will go in half the amount of times that 3 does, so 12. 7 doesn't go in. 8 will go in half the amount of times that 4 does, which is 9. Of course, we should know that one anyway, but there we go, and now they're both together, that's all the factors. So I want to look down this list, starting with the smallest number, because if the smallest one is the first one I look at, then that'll be obviously the question answered straight away. But of course, remembering that the alarm, the original alarm, is going to go off every 18 minutes. So that's going to go off at 18 minutes, it's going to go off at 36 minutes, it's going to go off at 54 minutes, and then it's going to go off again at 72 minutes. And we want the one that matches at 72. So starting with 1, well, 1's going to go off every minute, so that's going to match all of them. 2 is going to go off after 18 minutes, which obviously doesn't get all the way down to 72, so that's no good. 3 is going to go off after 18 minutes, so that's no good. 4 is going to go off after the 36 minutes, because 4 goes into 36, that's no good. 6 is going to go off after 36 minutes as well, so they'll match at 36. 8 is an interesting one. Let's have a think about 8. 8, 16, 24, 32, 40, 48, 56 doesn't match the 54, and then that is going to go off after the 72 minutes. So the value of Z is 8. That other alarm would be 8 minutes, and their lowest common multiple would be 72. It would be the next time that they would match. So there we go. That's quite a tricky question. It's almost a reverse lowest common multiple question, giving you the actual answer to the lowest common multiple, the 72, and getting you to figure out what that number could have been. Okay, so there we go. A bit of a reverse lowest common multiple question. For For question 7, we have an inequality shown on a number line, just a single inequality. So this one here, we will always write x first. So x is greater than or less than. Here it's greater than. The arrow actually points in the same direction that we need. So x is greater than, and the circle is sat above -1. So x is greater than -1. The circle's not coloured in, so we don't have to put the extra dash with our inequality symbol there. We just have x is greater than -1. For part B, we have to solve an inequality. There are unknowns on both sides, and the unknown on this right-hand side here is negative, therefore making it the smaller unknown, which I always tend to get rid of first. So to get rid of a negative unknown, we're going to add 2n to both sides. That means we're going to have 12 plus 6n is greater than 50. From there, we can take away the 12 so that the unknowns are only on one side. So we have 6n is greater than 38, and then dividing by 6, and 38 doesn't divide by 6 perfectly, so just leaving that as a fraction. You can try and simplify that if you want, but that is absolutely fine to leave your answer as a fraction, and there we go. If we did simplify it, they do both divide by 2. You could write 19 over 3, or you could write it as a mixed number, but you're not going to get any additional marks for that unless a question says give your answer in its simplest form or write your answer as a mixed number. Okay, there we go. On to question 8. Liam, Noah and Oscar share an amount of money in the ratio 2-3-5. Oscar gives some of his share to Liam and some to Noah. The money Liam, Noah and Oscar now have is in the ratio 4-5-3. Oscar now has £60 less than Noah. Work out the total amount of money Oscar gave to Liam and Noah. So this final line is the really important one here, because we're going to have to sort of work backwards, because we are now told that Oscar now has £60 less than Noah. And if we look, we have Liam, Noah and Oscar has £60 less than Noah. Now looking at the parts here, Oscar has 2 less parts. So those 2 parts in the ratio is equal to £60, and that's the start of our problem, because that now allows us to work out the value of 1 part. So of course we can divide this by 2. That tells us that 1 part is going to be equal to £30, and we can now work out how much money they have in total. So in this sort of, I say the first ratio, but it's kind of the second ratio, 4-5-3, but the first one that we are looking at, we can multiply all of these by 30. So the 4 parts is worth £120, the 5 parts is worth £150, and the 3 parts is worth £90. What we can now see is exactly how much money they have in total. So if we add all of these together, 150 plus 120 is 270, add the 90 is £360. Of course, take your time, use column addition to add those up if you need to. So they have £360 in total. Now the total never changed. Oscar just gave some of his money to Liam and some to Noah. And originally that was in the ratio 2-3-5. So this £360 we can actually now share into that original ratio 2, 3 and 5. Now in total there are 10 parts. So if we do 360 divided by 10, that tells us originally each part was £36. We can now times all of these by 36. We don't necessarily need to times them all, because we are just concerned with Oscars really. So if we label up these numbers, L, N and O, and the original Liam, Noah and Oscar, we really only need to look at that one at the end. So 5 times 36 is the key thing that we need to work out. So 6 times 5 is 30. 5 times 3 is 15, add the 3 is 18. So Oscar originally had £180. So in terms of how much money Oscar gave away to Liam and Noah, well, he started with 180, he ended up with 90, and 180 minus 90 is equal to £90, and that's how much he gave away. We could obviously write how much he gave to each individual person, but it's not actually asking that. It's just asking us the total amount that Oscar gave to Liam and Noah. So there we go, that's obviously just sharing in a ratio, but it was a sort of two-part or a two-step process there, thinking and working backwards into the past. And we had that sort of concept there with the £60 less than Noah and looking at the gap between the ratio. Of course, it could have said Oscar now has £60, something like that, in which case it would just be referring to the 3 in the ratio. But this one was £60 less than Noah, so it was looking at the gap there between the parts. So quite a tricky ratio question, but ultimately just sharing in a ratio. So a relatively nice one, even though the language of that question isn't the nicest. But there we go, that was question 8. Let's have a look at question 9. So we have a question here where we have 3 triangles. It says the area of triangle B is 12% greater than the area of triangle A, and the area of triangle C is 20% greater than the area of triangle B. And it asks us by what percentage is the area of triangle C greater than triangle A. Now the problem here is that we don't actually have any areas, there's no numbers. Now typically, whenever there's a question that has no numbers, I will always start with 100. So I'm just going to label A 100. And I do that because it makes the first percentage very, very nice and easy to work out. So if we increase that by 12%, then triangle B, when we add 12%, well 12% of 100 is just 12, which is why it's really nice in that very first step. Now that makes it really, really nice there. Now there might be a number that we could have picked where now getting 20% is really nice as well. But 20% isn't the worst to work out without a calculator. In this particular question, we are going to get some decimals because we need to work out 10% of 112, then get our 20% and then add it on. But it's not going to take us too long to do. So if I work out 10% of 112, I just need to divide it by 10, which is 11.2. I can now get 20% of 112 by multiplying this by 2, which isn't going to be too bad to do. We get 22.4, and that's what's going to be added on to triangle B to create the area of triangle C. So if I do 112 plus that 22.4, being careful here to line these up, 112.0, and if we add these together, we get 0.4, 2 and 2 makes 4, 2 and 1 makes 3, so it's 134.4, and that is the new area of C, of course, if A started as 100. So A could have started with any number, but the reason this works so nicely is because looking at the percentage change from 100 to 134.4 is very nice, because whatever number is added onto the 100 is just the additional percentage. So in this case, it's 34.4%, and that's my final answer. Now, had I have started with a different starting number, I might have had an easier way of getting that 20%. I mean, it wasn't too bad, but I might have had an easier way of doing it. But the final step of writing that increased percentage would not be as nice because it hasn't gone from 100. It wouldn't be bad without a calculator, but without a calculator, we definitely want to start with 100. So these types of questions, there's lots of different kind of ways you can see a question like this, but when you're not given a number and you're looking at percentage changes, just always start with 100. So there we go, it goes from 100 to 134.4. So our final answer is 34.4%. And there we go. And really all we actually had to do was add on 12 and then work out 20%. So not a difficult question there, and a nice 3 marks. Okay, on to question 10. Now it says here trapezium ABCD and trapezium EFGH are similar, which means that they are an enlargement of one another. So we have a scale factor that we'll want to look at between these. It says trapezium EFGH has an area of 135 centimetres squared. Work out the height h of trapezium ABCD. Now, first things first is the fact that these are similar. So we'll worry about the whole concept of the trapezium afterwards, because straight away we can see that these have a matching or a corresponding side here with the top of the trapezium. So to find the scale factor, I would do the bigger number, 12, divided by the smaller number, 8. And as it's a fraction, I'll simplify that. So divide the top and bottom by 4, we get 3 over 2, which is 1.5 or 1.5. So there's my scale factor. My scale factor between them is 1.5. And that may or may not help me. It should do, otherwise there'd be no point in telling us they were similar. Now it says trapezium EFGH has an area of 135, and that's the bigger trapezium. Now remember, the formula for the area of a trapezium is a half a plus b, which is the two parallel sides, multiplied by the height. Now we have most of the information within this formula. We're told the area is 135, which is equal to a half of a plus b. Now I tend to write this bit here as a plus b over 2. I just prefer it. Okay, you don't have to, and then times by the height. But it's written like half a plus b h in formula sheets. So a plus b is our two parallel sides, so 12 plus 18, which is 30. So we have 30 over 2 times by the height. Now 30 over 2 is 15, so we have 135 equals 15 times the height. And now we just need to work out how many 15s go into 135. So I can do some bus stop division for that, which doesn't really help because 15 doesn't go into 13. So I'll have to just do some multiples of 15 if I don't just know it. So 15, 30, 45, 60, 75, 90, 105, 120, 135. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9 times. So there we go. H is equal to 9. Now be very careful because that's the height of the second triangle here. So this second trapezium. So this second trapezium here has a height of 9. Now I can work backwards, almost going down to that smaller shape because I have the scale factor, which is 1.5. And now I have the scale factor of 1.5. I have the height of the larger trapezium. I can go down to my smaller trapezium by dividing by 1.5. And of course, I just need to know how many 1.5s go into 9, which again would probably just be easiest just sort of counting in 1.5s. We can do this to the side. 1.5, 3, 4.5, 6, 7.5, 9. So that's 1, 2, 3, 4, 5, 6. So there we go. That would equal 6. And that there is the final answer. That's the h that relates to the smaller trapezium, even though just being careful because we did have a h in our formula there, but h was the height of the smaller trapezium that we were looking at there. So there we go. That was sort of working backwards with the area of a trapezium formula to find the height of the bigger trapezium, and using similar shapes there with a decimal scale factor to go back to our smaller trapezium. So our final answer was 6. There we go, that doesn't have any units there either, so we do want to put our units with that. The height is in centimetres, so that would be 6 centimetres. Okay, on to question 11. Okay, so we have some density, mass and volume, and we have a mixture going on. So liquid X and liquid Y are mixed to make liquid Z. Liquid X has a mass and a density given to us. Liquid Y has a volume and a density given to us. It wants us to work out the density of liquid Z. So with a question like this, straight away, as soon as we see the word density in a question, you want to write down your formula. Density is equal to mass over volume. Or you can write that into a formula triangle, which does make it very quick in a question like this, just to quickly move between the different variations of the formula. So density, mass, and volume. Now with a question like this, I would pretty much always put it into a two-way table. Even if it's not a mixture question, it's a really nice way of organising a question just to see exactly what pieces you have been given. But we have a density, a mass and a volume. We have liquid X, liquid Y and liquid Z. So the information given to us is that we have a mass of X, and that is 240, and we have a density of 120. For liquid Y, we have a volume of 3, and we have a density of 160. And we want to work out the density of liquid Z. So we're looking to work out this box just here. Now remember, densities cannot be added together. When they are mixed together, we create a bit of an average between the two, and we're going to find out what that is. The only way to calculate a density is to get the total mass and the total volume, and then use our formula. Density is equal to mass over volume. So to start with, we can work out the volume of X. If you cover up the volume in your formula triangle, it's mass divided by density. So for this box here, if we show our working out, we have 240, the mass, divided by the density, 120. So that gives us a volume of 2, which is a very nice volume there, and that means in total we have a volume of 5. For the mass of y, that's density times volume, if you cover up your m in your formula triangle or rearrange your formula. So for this box just here, we want to do the 160 density times the volume of 3. Obviously take our time to work that out. We could just add together 3 of them. There we go, 0, 6, 12, 18, and then 4, so 480. From there, we can now work out the total mass. So we can add together 480 and 240. And obviously just notice how I am adding all my working out to the side, just to make it really clear exactly how I've got each of these numbers. 4, 5, 6, 7. There we go, so 720 is the mass. And now I can actually finish this question off and I can work out the density, because density is equal to mass divided by volume. So we have 720, the mass, the overall mass, divided by the overall volume of 5. 5 goes into 7 once, remainder 2. Goes into 22 4 times, remainder 2. And then it goes into 20 4 times. So our density is 144, and that is in kilograms per metre cubed in this question. So there we go, 144. The units are on the dotted line there, so I just need to write the 144. And there we go. So there we are, that is a density mixture question, just being very careful because questions like this typically do come up more frequently on calculator papers, but if they do come up on a non-calculator paper, just remember to get all of your information really organised. Even if it's about speed, distance, time as well, you can use a similar process and you can just make sure that all the information is really, really clear in front of you so you can see exactly what it is that you're missing. Okay. Question 12 is looking at a recurring decimal. Now this is a nice recurring decimal. It doesn't even ask us to write it in its simplest form, so it should hopefully come out as a nice answer. Now there's one recurring decimal here and one non-recurring decimal. So there are 2 different methods for solving a question like this. I take the approach, if there's only one recurring decimal, then I'm going to multiply it by 10. So x is equal to 0.47. I'm going to times that by 10. So 10x is equal to 4.77. I keep the recurring decimals balanced there so that they line up, and then I'm going to take these away from each other. So we have 9x is equal to, and I'm just going to do 4.7, take away the 0.4 sat above it, and that gives us 4.3. So 9x is equal to 4.3. We can turn this straight into a fraction. However, because we have that decimal involved, we are breaking a rule a little bit there. We've got to times the top and bottom by 10, so that there's no decimals in the fraction, and that gives us 43 over 90. So there we go. There's our final answer, 43 over 90. It says to express it as a fraction. We've done that. It says you must show you're working. We've done that. Just make sure, especially if you do use this method as well, that you show this times by 10 to show exactly how you got from 4.3 over 9 to 43 over 90. And there we go, that would be my final answer, 43 over 90. Okay, let's have a look at question 13. Okay, so looking at the first 5 terms of a sequence, and it says to find an expression in terms of n for the nth term of the sequence. Now I always like to rewrite the sequence so I can have a look at the difference between them. So we want to find the first differences to check to see whether this is a linear or a quadratic sequence. Of course, by looking at it, you can probably see this is a quadratic sequence. So going up from the first one, we have a difference of 7. Then we have a difference of 11. From 22 to 37, we have a difference of 15. We can keep on going if we want, but we can see we have a second difference here of 4. Now there are different ways to approach quadratic sequences, and I do like to initially make sure that we have a look at how the sequence is created, but at this point, particularly on the exams, it's really, really nice and it's a quick method just to use the formula that allows us to find the nth term nice and quickly. So any nth term is written in the form an squared plus bn plus c. And we've got some formulas that we can use to find the values of a, b and c. So the first formula is for the bottom line here, which is 2a is equal to 4. Now we can figure that out nice and quick. If 2a is equal to 4, then a is equal to 2. And that starts off our nth term formula. It'll be 2n squared. Now the next formula is for finding the middle row, and the formula for that is 3a plus b. Now, of course, we know what a is now. We know that a is 2, so 3a is 6. So 6 plus b is equal to 7. And if we take away 6 from each side, or just look at it logically, we can see that b is equal to 1. So now that b is equal to 1, we don't have to write the 1 in the nth term formula. We can just write plus n, because of course that means 1n. And now we can find the value of c. We get c from the top row. The formula is a plus b plus c, which is equal to 4. Now we know a and b. We have a is 2, so 2 plus b, which is 1, plus c is equal to 4. So that is 3 plus c is equal to 4, and therefore c is equal to 1. So there we go, our value of c is 1. We do put the number 1 for that, and there we go, there is our quadratic nth term. So 2n squared plus n plus 1, and there we go. So that's our final answer. We put that on our dotted line, so 2n squared plus n plus 1, and there we go. Okay, on to our next question. So this is just a small question here at the bottom of the page. It's Daniel has to work out the exact value of 81 to the power of a half. Daniel says a half of 81 is 40.5, so 81 to the power of a half is 40.5. Explain what is wrong with what Daniel says. Now obviously there is something within this that Daniel says which is correct. Half of 81 is 40.5, but a power of a half is not asking us to half the number. A power, the number within a fraction, within a power anyway, on the denominator is referring to doing a root. And in the case of a 2, that is a square root. So 81 to the power of a half is asking for the square root of 81, which is 9. Okay? Now we don't necessarily need to answer it. Obviously we can add as much detail here as we want. We can say that that is the answer 9. We can sort of say that Daniel has confused the power with halving. But ultimately, 81 to the power of a half is asking for the square root of 81, not 81 divided by 2. So obviously you can bulk up the language there, but that bit of information that I've written there would be the really key part, and that is looking at some negative and fractional indices. Obviously no negative in this one, and negative asks us to do the reciprocal as well. Just a fractional indice there, and making sure we know exactly what the rules are for those sorts of instructions within a power. And there we go, just a little 1 mark question there. On to question 15, we have some algebraic proof. Now it says here, prove that the square of an odd number is always 1 more than a multiple of 4. So when we are looking at algebraic proof, we have odd and even numbers. An even number is 2n, and an odd number is 2n plus 1. Now you can use other variations of this. I tend to stick with 2n plus 1. It helps to avoid some negatives as well. It asks us to find the square of an odd number. So when we square an algebraic expression like this is how we could write it. But of course, not forgetting that when you square something like that, it's a double bracket. So we have 2n plus 1 and another 2n plus 1. So we're going to expand this out, see what we get. 2n times 2n is 4n squared. 2n times 1 is 2n. 1 times 2n is another 2n. And then we get plus 1 at the end. And when we simplify those middle two pieces by collecting like terms, we get 4n squared plus 4n plus 1. Now it says to show that it's always 1 more than a multiple of 4. So you can probably see at this expression how it's always going to be 1 more than a multiple of 4 because we have this plus 1 at the end. But the way of showing that is to take the bits that can divide by 4, these bits here, and we're going to factor the 4 out, or factorise 4 out. So we get 4 lots of n squared plus n, close bracket, and then we'll just leave that plus 1 at the end. So we can say here that this will always be a multiple of 4, or 4, there we go, and then always plus 1 at the end. So there we go, a little explanation there that shows that you know what your algebraic expression represents. Does really help just to solidify that as you are being asked to prove it. Just a little written explanation at the end really helps. Now, you can have numbers that appear at the end that aren't just exactly the +1 as well. So you do have to watch out sometimes. As an example, if something came out like this, 4n squared plus 4n plus 5, that can still be shown, but when you take the factor of 4 out, and we get the n squared plus n, the 5 divides by 4 once and leaves a remainder of 1, and remainders can be left outside as well. Now, of course, that's a completely random expression there, but just sort of taking note that that can occur as well, where you have a little bit of a remainder left on the outside. But this was quite a nice one. It ended up with the +1 anyway when we'd expanded the bracket, so it's quite nice just leaving that +1 on the outside. And there we go, that was some algebraic proof. Okay, question 16 is looking at some column vectors. It says shape A is translated by the vector 3 minus 1, which means right 3 down 1. And then shape B is translated by the vector minus 6, 4, which is left 6, up 4. Describe the single transformation that maps A to C. So going from A, the very first shape, all the way to the very end after these two translations. Now the description is basically already written for us. We're going to have shape A is translated by the vector something to give shape C. So basically the description that we need to write is in there, we just need to figure out the vector. So if we combine these vectors, 3 and minus 1, and we add to that the next movement, minus 6 and 4, our overall resultant vector, 3 add negative 6 is negative 3, negative 1 add 4 is positive 3, that's our vector there. So we're just going to replicate the description that's already given to us. We've got shape A is translated by the vector minus 3, 3. And we'll just write that in, minus 3, 3. There we go. And you could say to give shape C as well. But shape A is translated by the vector minus 3, 3 is the description of that single transformation. Okay, part B, we have describe fully the single transformation that maps triangle A to triangle B. So going from the larger triangle here to the smaller triangle. Now, this is, if you can spot what's happened here, you can see that the triangle has both rotated and it's gotten smaller. Now that, of course, would be two descriptions, and it says a single transformation. So the transformation that we sort of refer to when this sort of thing happens is an enlargement. But this is an enlargement by a negative scale factor. So you need to know these very well. They're nice and easy to find out, but it's just one of those ones you need to sort of know, because you don't want to be saying it's been rotated and it's been shrunk or enlarged by a number. So we do want to get it in one transformation. So to find this, we're going to join up the corresponding points. So we have this point here and this point here. Now they're joined up. So if we join those up, of course using a ruler and a pencil, and then we're going to do the same for the other 2 points here and here. We're going to join those up. Now you'll see there where those points cross over, that is our centre of enlargement for this negative enlargement that we're going to write about. So this is an enlargement, and we're going to write that first. So there's an enlargement by the scale factor. And now we're going to have a look at the shapes and figure out how much smaller it's got. So this side here currently has a length of 3, and the corresponding side over here has a length of 1. So it's 1/3 of the size. Now because it's a negative enlargement, that means it's going to be minus 1/3. So enlargement by the scale factor minus 1/3, and then we're going to say from the point, and we're going to say the centre of enlargement. You can say from the centre of enlargement or any sort of phraseology like that, but this coordinate here is the coordinate 2, 2. There we go, so that would be from the point, and we'll just say 2, 2. Now, of course, you could be asked to do something like this going from triangle B to triangle A as well. Now, the only thing that would change there is the actual scale factor, because if it's getting bigger, if I'm going from 1 to 3 instead, the scale factor would have been minus 3 there. Again, incorporating that minus, as it is a negative enlargement, it's going back through the point. But there we go, that is our description for that one. It's an enlargement by the scale factor minus 1/3 from the point to 2. Okay, our next question is a distance time graph that shows some information about part of a car journey. We've got distance travelled on the left and the time down the bottom, and we've got this curved graph. So it says here to find an estimate for the gradient of the graph at 5 seconds, and you must show how you get your answer. So at 5 seconds, I'm going to mark a dot on the graph, and we need to draw a tangent at this point. So to work out the gradient, we have a formula which is rise over run, or the change in y, divided by the change in x. Now to do that, we have to draw a very, very neat tangent, which isn't ideal for me on the screen. But what we would do is place a ruler sort of on the inside of the curve until we can just see the dot above the ruler. So there we go. I think I've drawn that one relatively well there, but every tangent is going to be slightly different. Now when we're doing this on a non-calculator paper, we want to make sure that the division that we do is going to be a nice one. We can leave our answer in terms of a fraction, but ideally we want the base of our triangle that we're going to draw in to be 1 or 2. 2 is fine. Ideally, if we went across here, so I've gone from 4 to 5, just so the run there is 1, and then I could draw a line up and find the change in y. Now I could go across further, I'd probably get a slightly more accurate answer. So if I go across another square to 6 and then up, I get quite a nice number there as well. Again, it's completely up to you. I'll have a look at both and we'll see what numbers we get. But if the run there is 1, I'm going to have to trace along very carefully and figure out what number this is. And the top of the triangle, trace along and figure out what number this is. So let's have a look at that. Now it goes from 0 to 20 on the left there on the axes. There are 5 squares, so each one's 4. So that's 4, 8, 12. And then 24, 28 just here. There we go. So that has a rise that goes from 12 to 28, and that is 16. So that's a rise of 16. So my gradient there is 16. Now, if I had extended slightly further, it's a bit of a pain because we're going to have to count all of that again. But if I'd have done a slightly bigger triangle, I might get a slightly more accurate answer here. And if we trace along and see where that goes to, so that's 44. So from 12 to 44 is a rise of 32, and then it would have been 32 divided by 2 instead. So actually I'd have got the same answer. So that's good. That means it's relatively accurate as well. Now, of course, if you've got this printed off and you're doing it on paper, yours might be either side of that. There is some leeway that you're allowed. It doesn't have to be perfectly 16. Mine might not be perfect, but it should be somewhere close to that. So my answer there is 16 for my estimate for the gradient of the graph. And obviously it does have this word estimate because we are just drawing our own tangent, and our tangents can be different. We are not computers, we're not doing them perfectly, so it is just an estimate. Now it says in part B here, what does the gradient of the graph represent? Now any gradient on a graph like this represents the change between the two things. So in this case it's the change in distance over time. Now a change in distance over time, if we think about the division that we've actually done there, we've done distance divided by time. That's what the change in y was, the distance, and the change in x was the time. And distance divided by time is speed. That is literally our formula for speed. It's equal to distance over time. So for part B here, the gradient represents the speed. Well, what was it about? It was about a car journey. So the speed of the car at 5 seconds. And there we go. So that's what the gradient represents on a distance time graph. There are obviously different types of graphs. You can have different things, but it represents the change in one thing comparatively to the other. In this case, the change in distance over time. Okay, on to our next question. Okay, so in this question it says here is a triangle, PQR, and we can see the triangle there. We've got 2 of the angles and the length of 6. And it says work out the exact length of PR. Now, of course, questions like this, hopefully you've seen previously where these questions that you would normally expect to see on a calculator paper end up appearing on a non-calculator paper. And that sort of triggers that we're going to need to use some exact values of trigonometry. So we want to switch our brains onto sort of calculator mode in terms of what form of trigonometry would we apply to this question. Now the length P to R is down the bottom here. So we want to just have a quick test to see which form of trigonometry this would be. So to do that, we'll check pairs of opposites. So there's a pair of opposites here, and there is a pair of opposites here, obviously with the one unknown, and that gives us a massive hint there that this is going to be using the sine rule. Now the sine rule for side lengths is A over sine A is equal to B over sine B. Now in this one here, we want to put these pieces into place and let's see what we've got. So we want to label this up. Let's call the X the A, with the opposite angle being the big A, and the other one that we're using 6 as B, and the opposite angle big B. So we have X over sine 60 is equal to 6 over sine 45. So there we go. There is our sine rule. Now, with this, when we have these values of trigonometry, we should hopefully recognise things like 60, 30, 45 are all those exact values that we need to learn. Now, of course, I'll link a video in the description for the calculations behind the exact values of trig, but it can be quite helpful just to learn these. So for sine 60, the value that we use is root 3 over 2. We also have sine 45 in this one, and sine 45 is root 2 over 2. So they're the exact values that we're going to need to use. Now in both of these, that just means that we have a division that we have to do. So if we look at the one on the left to start with, we have x divided by sine 60, which is root 3 over 2. And on the right, we have 6 divided by sine 45, which is root 2 over 2. So we can apply our fraction rules here. We'll have it as x over 1 and 6 over 1, and we'll just multiply by the reciprocal. So we will do x over 1 times by 2 over root 3. And that gives us 2x over root 3. And that's the first bit on the left. On the right, we have 6 over 1 times 2 over root 2, which is 12 over root 2. So it says that these two are of course equal to one another. So using the sine rule, again, these are equal. So 2x over root 3 is equal to 12 over root 2. So we can go about trying to solve this. We can cross multiply to move these pieces left and right. So if we times both sides by the root 3, we get 2x is equal to 12 root 3 over root 2. Again, that's just timesing by root 3 to get rid of this fraction. Now what we actually want is the value of x. So we're actually pretty close to the final step here. If we want the x, if we want it to say x equals, then at this point we would need to divide by 2. Now dividing by 2, of course, nice and easy. If we have a nice fraction to divide by 2, we don't have the nicest looking fraction here. So we could, instead of dividing by 2, you can just write times by a half. Again, what we've done before, if you're dividing by 2, that's the same as timesing by 1 over 2. So x will equal, again, it isn't too difficult to divide that by 2, but as we've applied this method of using the reciprocal when dividing, we can just times by 1 over 2. You'll see what happens to this fraction anyway, because it becomes 12 root 3 over 2 root 2, and then you can divide the top and bottom by 2, which gives you 6 root 3 over root 2. So again, when you divided by 2, it did just halve that numerator there. The 6 came from the 12. So 12 root 3 over root 2 became 6 root 3 over root 2. So that is the exact answer, 6 root 3 over root 2. If you wanted to, you could rationalise the denominator. Don't necessarily need to in this question, but we could rationalise the denominator here. You could times the top and bottom by root 2, and that would give you 6 root 6 over 2, which is 3 root 6. So either one of these answers would be fine. I'm going to write the answer as to 3 root 6 because it's just a little bit neater. But the first answer that we wrote, this 6 root 3 over root 2, would be absolutely fine as well. So there we go, a pretty tricky question there, looking at exact values of trigonometry and using the sine rule without a calculator. So there we go, pretty tricky. Definitely need to know your exact values of trig, and as I said, I'll link a video in the description for that. But there we go, there is quite a tricky non-calculator trigonometry question. Okay, so looking at some algebraic fractions. So this one asks us to solve these algebraic fractions. It says to give it in the form p plus or minus root q over 2, where p and q are integers. Now this does give us a massive hint here. This plus and minus gives the same huge hint that we're going to be using the quadratic formula, but we're just going to be leaving the numbers in the quadratic formula. That's the only place we tend to see that symbol, other than when sometimes we're solving by completing the square. So in order to solve this, we're going to need to first add together these algebraic fractions. So just looking at this first bit to start with, we need to make a common denominator. So we're going to times the left fraction by the right denominator, x minus 1, and we're going to times this right fraction by that left denominator, 2x minus 1. Now when we do that, we get 1 times x minus 1 on the numerator of the left fraction, and we'll have a double bracket, 2x minus 1 x minus 1. I'm going to add that to 3 lots of 2x minus 1 over that common denominator, 2x minus 1 and x minus 1. Now of course that's all equal to 1, we don't want to forget that, but I do want to simplify this first and sort of get it all put together before we worry about that equaling 1. So if I expand the numerator on the left fraction, we just have x minus 1, and we can expand this double bracket on the bottom. I'll kind of do it all in one jump if I can, so that would be minus 2x on that bit there. That would be minus 1x. So we end up with 2x squared minus 2x minus 1x is minus 3x, and negative 1 times negative 1 is plus 1. So there's my denominator, that's the same on the other fraction as well. We'll expand the other numerator, so 6x minus 3, and that's all over 2x squared minus 3x plus 1. And now we can add these both together. So if we add these together, let's do this over here, we have 1x and 6x, which makes 7x. Negative 1 add negative 3 is negative 4. That's all over that denominator, 2x squared minus 3x plus 1, and now all of that is equal to 1. So we've added the algebraic fractions together. In order to solve it, it needs to equal 0. We've got a quadratic here, it's got to equal 0. Thankfully on the right it's only a 1, so we can times this denominator to the right and it will just be that denominator, because when we times it by 1 it doesn't change it. So we end up with 7x minus 4 is equal to 2x squared minus 3x plus 1. We can now make it equal 0. I'm going to move these pieces to the right, so I'm going to minus 7x and add 4. That's going to minus 7x from this 3x, and it's going to add 4 to the 1. That gives me 0 is equal to 2x squared minus 10x plus 5. Right, I've got my quadratic. It's equal to 0. I have a equals 2, b is equal to negative 10, and c is equal to 5. We can now put that into the quadratic formula, which is minus b plus or minus the square root of b squared minus 4ac all over 2a. I can now substitute these pieces in, so minus b becomes positive 10, so we have plus 10 at the start, plus and minus the square root of, we're going to have 10 squared, which is 100, minus 4 times 2 times 5, and that's all over 4. Okay, we just need to simplify this. 4 on the bottom there because it's 2 times 2, so we have 10 plus or minus the square root of, and we have 100 minus 4 times 2 times 5. 4 times 2 is 8, times 5 is 40. So that is 100 minus 40, which is 60. and that's all over 4. And let's just have a quick look how close we are. So give your answer in the form p plus or minus root q over 2. At the moment ours is over 4. First of all, we're going to need to simplify this surd so that we can divide the top and bottom by 2, because at the moment we can divide the 4 by 2, we can divide the 10 by 2, but we're going to need an even number in front of that surd in order to divide that by 2 as well. So square root of 60 is the square root of 4 multiplied by the square root of 15, which is 2 root 15. There we go, we've got the 2 there which will divide. So if we rewrite this before we simplify it, we've got 10 plus and minus, let's actually put the 2 in there, 2 root 15 all over 4. We can now divide the top and bottom by 2, which gives us 5 plus and minus root 15 all over 2. And there we go, let's just double check the way it wanted the question was a number plus or minus root another number where it's an integer all over 2. And that's the form that we've got there, 5 plus or minus root 15 all over 2. And there we go, there was solving our algebraic fraction and using a bit of the quadratic formula, which again is normally considered to be a calculator topic, but just goes to show how you can apply it still in a non-calculator question. Okay, on to our vectors question. Okay, so the question says OABC is a parallelogram. O to A is A, which we can see, and O to C is C, which we can also see on the bottom there. X is the midpoint of the line A to C. Now that's something that's not drawn on there, so we could draw that in. And the midpoint is around here, and we'll call that X. OCD is a straight line, so that O to C, C to D is K to 1. So it's saying that this line O to C is extended, and somewhere over here, doesn't really matter how far in terms of our drawing, but somewhere over here there is a point D. And it says that O to C, C to D is K dot dot 1. So the ratio of the two sides there. It also says, then down below, given that x to d is 3c minus a half a, find the value of k. Okay, so it wants us to find the value of that ratio. So let's have a look. So x to d is another line which has just been given to us. So x to d is over here, and it says that that is 3c minus a half a. So this here is 3c minus a half a. Okay, so in order to find the length of the line, we need to find the length of the line C to D. So that we can compare the ratio, we know that the O to C is 1C right here, but we just need to find out how many C's this little stretch of the line is here. Of course, it might be bigger than 1C, but until we figure it out, we're not going to know. So it doesn't really matter that our diagram isn't necessarily drawn to scale, it's just a visual representation for us. Now what we can do is we can actually figure out what some of these lines are, and we need to find two different ways of sort of getting to point D from another point on the diagram. So you need to have a look at the diagram and think about what ways that we could get there. Now one way that we could get there is we could go from A to X to D. That's actually a vector that we can work out. Another way that we could get there, if we do this in a different colour, we could go from A to O to C, and then this extra little bit that gets us to D. So if we think about that as a journey, and we think about the actual vectors that we'll need to do so, hopefully we'll be able to find a missing gap in one of them and sort of find that missing piece, which will hopefully tell us how far it is. So if we start by going from A to X. Now in order to get from A to X, we're going to have to go from A to C. It says that X is a midpoint, so we can do half of that vector, and that'll be from A to X. So A to C is equal to, and if we look at the diagram, we have minus A and plus C. Minus A plus C can also be written as C minus A. Or minus A plus C if you prefer writing it the other way around. We can now do the midpoint, so A to X is half of that. So we could write that as a bracket, half bracket c minus a, or we could just times them both by a half, half c minus half a. From there, we can now get to d, because we are given the vector to get from x to d. So now we have moved to this point, we can now use the vector that's already given to us to get to point D. So if we do A to D, that is A to X plus the X to D we've already been given. So half C minus half A plus 3C minus half A. Now if we simplify that, we have a half C and a 3C, so that's 3.5C. Minus half A is just minus A overall. So we have 3.5C minus A. I typically wouldn't write mixed numbers, so we'll write that as an improper fraction. 3 times 2 is 6, plus the 1 is 7. So 2 and 7, 7 over 2C minus A, and that is the vector A to D. So if we can do that exact same movement, but using a different path, so rather than moving down from A to X and then X to D, we'll do it via a different path and we'll see what's missing. So the new path that we're going to take, we're going to go from A to O and then from O to C, which is a nice easy vector. We've already worked out A to C, that is C minus A. And then we'll have a look at what's missing just to get this last little bit here along to D. So A to C, we have already written down. A to C is C minus A. A to D, and here's where we have to sort of consider the direction of the line. Now that line is an extension of O to C, and C is just this little vector here going from O to C. So C to D, the bit we're trying to find, is a certain amount of C. It could be a whole number, could be a fractional amount, could be just another C. But that's what we're going to figure out. How many C's is it to get along from C to D? What's the length of that line? So A to D is, and let's call it, and let's pick a letter for this, let's just call it Y, as we already have every other letter, mainly. We've got the X as well, we've got the K in the ratio, so we don't want to confuse the letters. So we have Y lots of C plus C minus A, and that is the overall little vector. Now this bit here, YC plus C, has to match this 7 over 2C. We've got the minus A in both of them. We just want to know what the difference there in terms of the C's is. So if we look at this YC plus C, well, this is 1C right here. So what we have is Y plus 1 in terms of the numbers in front of C. Y plus 1 has to be equal to 7 over 2. Or you could write that as 3.5, completely up to you. So if we take away 1 from both sides, we get that Y is equal to, and taking away 1 from 7 over 2 gets us to 5 over 2. We're just taking away, essentially minusing 2 over 2. So Y is equal to 5 over 2, which is 2.5. So that there is 5 over 2C, which of course is actually longer than the original line that we'd drawn, so we're definitely not to scale, it would be much further along to the right, but we figured out the distance, and that is 5 over 2C. So, the final step here is to look at this ratio, because at the moment, O to C, C to D, in terms of the amounts of C's that we have, we've got 1C from O to C, again, this one just here, so that's 1, and then we have 5 over 2 just here. So our ratio at the moment is 1 dot dot 5 over 2. Or we could write that as, again, 2.5. Now it says that it can be written K to 1. So it wants us to have the ratio as something dot dot 1. Now in order to get 1 on the right hand side, we would have to divide by 5 over 2. Whatever we do to the right, we've also got to do to the left. So divide by 5 over 2 as well. We can work that out to the side. 1 divided by 5 over 2 is 1 times 2 over 5, which is equal to 2 over 5. So there we go. Our value of K is 2 over 5. and that's our final answer there. So that'll be our final answer. We would say k equals 2 over 5, and that would be the final answer to this question, k equals 2/5. So quite a tricky question there, because even if you are good at finding the missing vectors, there's quite a difficult step at the start, which is actually just thinking about how you're going to approach it. And that's probably the hardest part with vectors. But as with all questions like this, especially towards the end of the exam, and especially with vector proof, you just have to practice lots of questions. And once you've practiced lots and lots of questions, you've seen lots of different variations, it does really, really help with the ideas behind how you start to approach these questions and find those missing pieces. So again, I will link a video obviously for vector proof in the description, so there's lots in there that you can actually check out. It is a very difficult topic, but there we go, there was a nice question on vector proof. Okay, question 21, we are looking at rationalising surds. So this is quite a nasty looking one. We have a surd on the left, add this surd on the right. It says it can be written in the form a plus b root 2, where a and b are integers. Now in order to do this, we're going to need to rationalise these fractions, we're going to need to make a common denominator, we're going to need to add them together, and we need to hope that it just ends up being a plus b root 2. Now the first thing to notice is this fraction on the right is a really nice easy one to rationalise. So we're going to do that first. 4 over root 2 times the top and bottom by root 2. It's basically done in a few seconds, dead easy. That becomes 4 root 2 over 2, which is 2 root 2. So that's the first half done, and that's dead easy. Now hopefully the one on the left is going to rationalise to something nice, and adding that to root 2 there won't really feel like much of an effort. It does look worse than some other questions, but that's, well, half of it done technically, but definitely the much easier half. So let's have a look at this one. We've got our much harder one here, 6 plus 2 root 2 over 2 minus root 2. So we need to times the top and bottom by 2 plus root 2. Remember, the same as the denominator there, but just changing the sign. So 2 plus root 2. We need to take our time, just expanding the top and the bottom. I'm going to go do the bottom first. 2 times 2 is 4. The middle two cancel each other out because we get plus 2 root 2 minus 2 root 2. So they cancel each other out. And then root 2 times root 2 is 2. It's positive times negative. So 4 minus 2 as the denominator, which of course is just going to be 2, but we'll rewrite that in a moment. The numerator, we have 4 multiplications to do, so 6 times 2 is 12, 6 times root 2 is 6 root 2, 2 root 2 times 2 is 4 root 2, and the final step there, 2 root 2 times root 2, that's always the bit that I do to the side, so that becomes 2 root 4 is 2, so it's 2 times 2, so we just get 4 at the end. Okay, so I've expanded the numerator and the denominator of that fraction. So now we want to simplify it. So collect the like terms. So it's 12 plus 4 on the top is 16. Plus, and then we have 10 lots of root 2 in total there. The 6 root 2 and the 4 root 2. That's all divided by 2. And both of those whole numbers there will divide by 2. So this is going to simplify. So it's looking like it's going to work the way we want it to, which is always a good sign. That's going to give us 8 plus 5 root 2, and that is our first fraction now rationalised and not even written as a fraction anymore because of the fact that it's simplified, which is perfect because our final answer, it doesn't want it in fractional form. So we have 8 plus 5 root 2. The previous one was 2 plus root 2, so we're going to add that. So 2 root 2, there we go, and once we add all of those together we get 8 plus 7 root 2, and there we go, there is our final answer. Nice and easy, that final step there, just adding that additional 2 root 2. We've got our answer in the exact form that it wanted, a plus b root 2, where a and b are integers. We've got 8 plus 7 root 2, and there we go, and there's our final answer. So rationalising surds there, actually not the worst question, even though it looks really bad. It's actually quite a nice one there because the second fraction, dead easy to rationalise, and that first fraction there, although you've got to watch out for this little step here with this bit, other than that, relatively nice in terms of the rationalising. And there we go, 8 plus 7 root 2, and that is our rationalising Surds questions. Let's write that on the dotted line. 8 plus 7 root 2. There we go, and there's our final answer. Okay, and on to quadratic simultaneous equations. Okay, so you can tell just by looking at this one that it's not going to be an easy question, mainly because we have coefficients of x squared and y squared, and that second equation there is not an easy y equals or x equals. So we're going to have to rearrange this second equation to make it y equals or x equals, substitute it into the top one, and we're going to have some fractional sort of expressions that we're going to need to simplify. It's not going to be the nicest question at all. But let's start by rearranging this second equation. So dividing both sides by 2, we get y is equal to 4x minus 1 over 2. Now you can write that as 2x minus 0.5 or 2x minus a half. I tend to prefer to leave it as a fraction. I think you'll see why as we go through, but I just want to avoid having lots of fractions to sort of expand, and it doesn't actually work out too horribly having a fraction that we substitute in. So I'm going to put that y in place of the y here with the y squared. I'm going to just write it out. So we have 4x squared plus 4 lots of 4x minus 1 over 2, and that is squared, and that equals 65. Now that bracket there where we square that, on the numerator we are going to have to do 4x minus 1 squared, which is going to be a double bracket. So I'm just going to work that out to the side, 4x minus 1 and another 4x minus 1. That gives me 16x squared minus 4x minus another 4x, which is minus 8x, and then plus 1. So that's what the numerator is going to be when we expand it. So let's expand that. We have 4x squared plus 4 lots of, I'll keep it in a bracket because we still have to times it by 4. So we get 16x squared minus 8x plus 1. The denominator 2 times 2 gives us 4, and that equals 65. Now I've just noticed actually something quite interesting happens here, because we're going to multiply by 4 what's inside the bracket, but what's inside the bracket is getting divided by 4. So technically that actually cancels each other out. So normally what I would do is now times the numerator by 4, but as I'm then going to divide it by 4 anyway, actually what happens is this piece and this piece cancel each other out. So quite a unique question there. So we have 4x squared plus, and because they just cancel each other out, we have 16x squared minus 8x plus 1 is equal to 65. We can now join together these two like terms here. That's dead easy to do in one step, so I'm also going to minus 65 because we need this equal to 0. So we'll do both of those in one step just to avoid writing out this line over and over again. So we get 20x squared minus 8x minus 64 equals 0. So we've got our nice quadratic now that's equal to 0. We just need to factorise this to solve it. Now, if we can, we want to divide everything by a number. These all divide by 4. So if we divide by 4, that gives us 5x squared minus 2x minus 16 equals 0. From here, we can factorise. We are going to have a 5x in one of the brackets and a 1x. The factors of 16 are 1 and 16, 2 and 8, or 4 and 4. We're trying to make negative 2 in the middle, and one of those numbers is going to get multiplied by 5. So 1 and 16 would be 5 and 16. We can't make 2 with that. 2 and 8 would be 10 and 8. That would work. So we want the 2 to go over here, 8 to go over here. We want minus 2, so let's make the minus 10 plus 8. And there we go, that gives us our two values of x. So the one on the right's dead easy, x is equal to 2. The one on the left, we have x is equal to negative 8 over 5. And that's not going to be very nice at all, particularly as to find y, we're going to have to substitute into that fraction at the top there. So we've got our values of x. We've actually done the vast majority of the question here. Very, very nice that at this stage here, the 4's cancelled each other out. That saved us having to write another couple of lines of working out. just made this seem a little bit nicer, even though it's a very challenging question, a little bit nicer than it potentially could have been. So if we substitute these values of x in, we have our y equals formula up here. Let's go with the x equals 2, as that's obviously nicer to substitute in than negative 8 over 5. So when x equals 2, y equals 4 times 2, which is 8, minus 1 over 2, which equals 7 over 2, or you could write that, of course, as 3.5. So there's our first set of values, x equals 2 and y equals 3.5. There we go, let's highlight that so we don't lose it. And then for our next set of values, we need to substitute x is equal to negative 8 over 5 into that. So when x is equal to negative 8 over 5, if you prefer working with decimals, you could actually convert that to a decimal now. I'm going to leave it as it is and just see what happens. So 4 lots of 8 over 5, or 4 times 8 is 32, so that's minus 32 over 5, minus 1 all over 2. So 1, of course, is 5 over 5. So minus 32 over 5 minus 5 over 5 is minus 37 over 5, and that's all over 2. Now that dividing by 2, again, can be written as divide by 2 or times by a half. So that's minus 37 over 5 times a half, which is minus 37 over 10, or minus 3.7, if you want to write that as a decimal. So minus 3.7. Right, there we go. You could leave that as a fraction as well. It doesn't say anywhere that it has to be simplified. So we have x equals minus 8 over 5 and y is equal to minus 3.7, or any other variation of ways that you want to write that number. You don't have to write it as a fraction, you don't have to write it as a decimal, either one's absolutely fine. But there we go, there is our second set of solutions. So we've got a lot of solutions there. Of course, you want to make sure that your answer is nice and clear for this, so we'd want to write x equals 2, y equals 3.5, and x equals negative 8 over 5, y equals negative 3.7. So there are different ways that dotted lines can give this to you. This one's got a long dotted line, so we'd write the whole thing. Sometimes it says x equals ... y equals ... and then gives you a second below that, and of course you just write them all in the right place, making sure that you pair them up. If it's a long line like this, then just write them as a list. So x equals 2, y equals 3.5, and then the second set of solutions next to it. But there we go, there's our final answer for that one. Definitely a very tricky question there where you had to actually rearrange it. But as I said, a nice aspect there where we've highlighted the 4s, the fact that we times by 4 and divided by 4 that cancelled that step out did just mean that there was a lot less working out there. But a difficult one to factorise, a difficult one to then substitute in as well, particularly without a calculator. But there we go, a good challenging quadratic simultaneous equation as that final question. And there we go, that is the end of our paper. So there we go, that was the end of this paper 1. Of course, we'll have more content coming out before paper 2 and 3, but otherwise, good luck on your first exam, and I'll see you for our next video looking at papers 2 and 3, where we'll have lots of practice for all of the topics that don't appear on paper 1. One of the most common requests I get from students is for specific advice on how to revise for exams. So today's video covers my 5 top tips for GCSE maths exams. Tip 1. My grade calculator. Go to my website and complete my grade calculator to get your estimated working at grade, so you can get an idea of your starting point. You'll be able to answer common exam style questions from either of the exam tiers for higher or foundation, and once you've completed that, you will receive a report which gives you that estimated working at grade, so you can start to look at your next steps. Tip 2, my ultimate revision guide. Go to my website and request all of my free resources. Then once you receive the email, download the attachment and complete my ultimate revision guide so you can practice every single topic that can appear on the exams and make sure that you know exactly what to do next. Tip 3, my revision checklist. Once you've completed my ultimate revision guide, use my revision checklist to identify the topics that you need to prioritise, so that you can work through those specific video lessons available for free on my YouTube channel. Tip 4, my practice papers and booklets. Once you've worked through the YouTube lessons, then you need to work through the practice papers and booklets to solidify your understanding in preparation for the exams. You can download these from the website, and there are video solutions to accompany each booklet. Tip 5. My rapid revision system. Alternatively, if you need a time-efficient approach due to the other subjects that you need to revise for, then you should sign up for my rapid revision program upgrade, as it combines all of the benefits of the 4 previous points but turns them into a personalised revision plan, which means all you need to do is complete my revision quiz and you'll know exactly which lessons or topics you need to work on to maximise your maths in minimum time. This is my paid program, but you can sign up for a free trial on my website now. And if you feel like you need top tier support direction from me, then sign up for my live weekly interactive lessons, which include revision specific lessons focusing on the topics that I expect to appear in exam papers 1, 2 and 3. Right now there is a special offer, and the next 20 people who sign up for live will get 100% free access to my upgrade program as well, which means that you will have complete access to all the best resources that can help you achieve the grades you need to take you onto the next phase of your educational journey.